Hello, everyone, and welcome. Thank you for joining our webinar. My name is Donald Stahl from Shimadzu's Materials Testing Division, and I will be your host for today. For today's topic, we will be discussing strength evaluation techniques of lithium-ion battery components. But before we start, I would like to introduce you to the webinar's features and windows. Starting on the left side of your screen, you will notice the slides window where you can view today's presentation. Directly below that are resource links that will navigate you to additional resources related to today's topic. In the center of your screen is the Q&A window. Please submit questions through the Q&A window at any time during the presentation. We will not be answering questions live after today's webinar, however, we will follow up with an email. On the right side of your screen, you should see a set of survey questions. Please take a moment to answer the questions at any point or before or after the webinar. Your responses are truly appreciated and they help us tremendously. Finally, at the bottom of your screen are icons that can restore windows in the event that they are closed or minimized during the presentation. It is now my pleasure to introduce our presenter for the day, Dr. William Gabler. William Gabler is a senior application scientist in the material science group at Shimadzu Scientific Instruments. He joined the company after obtaining his PhD from North Carolina State University, where he researched mechanical and chemical test methods for polymers and textile products. At Shimadzu, he is responsible for supporting sales and applications, training customers, and researching new applications. He helps support mechanical testing, fatigue, thermal, particle size, hardness, rheometry, and X-ray instruments. William, thank you for joining us today. What do you got for us?
Thank you for that introduction, Donald. Today I'll be discussing some strength evaluation techniques for lithium-ion battery components using Shimadzu testing machines. First, I'll give a brief overview of the structure of a lithium-ion battery and its components. Then I'll give some examples of mechanical testing of separators, including tensile, puncture, and compression testing. And then I'll discuss how to characterize electrode materials, specifically compression tests of active materials and powders used in solid-state batteries. Lithium-ion batteries have been in use since the 90s, and their constant development has resulted in increased energy density and decreased costs, so that now they're the most commonly used rechargeable batteries in modern electronics and being used to power electric vehicles. They consist of two electrodes, a positive cathode and a negative anode, that are separated by a porous film called the separator. During charging, the positive electrode, which is made of a lithium metal oxide, is oxidized, causing lithium ions to travel through the separator, where it's stored within layers of graphite. During discharge, the reverse happens. The lithium leaves the anode and recombines with the metal oxide in a process called intercalation. And this causes a flow of electrons through the circuit that can power the electric device. Taking a closer look at the inner structure, this slide shows the layers of materials typically used in a lithium-ion battery. Each electrode is prepared by creating a slurry of electrode material, which is a fine powder, and mixing it with a solvent along with additives such as conductive aids and binders. The slurry is coated onto the collector films, which are typically copper and aluminum foils, and then cured. The two layers can then be layered together with a separator between them and assembled into various battery shapes. For instance, the layers may be rolled into a cylinder or folded to make a square battery pack. During manufacture and use, each component may be subjected to various stresses. Some components also swell and heat up during the process of charging and discharging. This means that it's important to test and characterize the mechanical properties of each component material. For the first few examples of mechanical tests, I'll be showing some tests that can be performed on the separator material, which separators are typically polyethylene or polypropylene films that are created in a process of extrusion. In this example, we measured the tensile strength of two different separators by preparing them in dumbbell shapes and performing a mechanical tensile test on each dumbbell at 3 different temperatures, 25 degrees C, 60 degrees C, and 90 degrees C. This slide shows the results of the strength and elongation at failure for the 2 separators at various temperatures. As I mentioned, these types of films are typically manufactured by extruding and stretching the film as it's produced. This direction of stretching along the length of the film is referred to as the machine direction, and the width is referred to as the transverse direction. The stretching produces alignment within the polymer that tends to increase the strength and stiffness in the machine direction. So the first thing I'll point out is that both separators showed significant differences when tested in the transverse and machine direction. The difference is much larger for separator 1 than for separator 2, indicating that separator 2 may have been manufactured in a biaxial stretching method. Next, we can look at the results at various temperatures, going from room temperature to 25 to 90 degrees C. In the stress-strain curves, we can see that all of the films showed significant decrease in strength and an increase in the amount of elongation before failure. Notably, though, when going from 25C to 60C, the mechanical strength of both films does not drop significantly, indicating that the films mostly maintain their mechanical strength. However, when increasing to 90 degrees C, it causes a drop almost in half in most of the mechanical strengths. Next is an example of the puncture strength test of a separator material. Since separators are packed densely inside the battery, it's necessary to determine the strength of the separator against a puncture to prevent it from being punctured by electrode materials or during manufacturing. The photo shows an image of a puncture test where the film is clamped into a lower ring, and then a small probe is pressed down on the sample until it breaks through the separator. The test force and stroke are measured as the spherical probe with a 1 millimeter tip penetrates the separator. The tests were conducted again at 3 different temperatures of 25, 60, and 90 C. Comparing the results from 25 to 60 C, we can see that the maximum test force again is very similar, but the maximum displacement increases at 60 degrees C. And then next, comparing 60 to 90 degrees C, we can see that the maximum test force decreases, but the maximum displacement is the same. From above, it can be seen that the lithium-ion battery separators in this test has an increase in elongation, but no decrease in strength up to 60 C. It may also be useful to measure the Poisson's ratio of a separator film, which is the reduction in width as a material is elongated. In this example here, we show that it's possible to measure the Poisson's ratio of a separator film in a tensile test using a non-contact extensometers. Non-contact extensometers, such as the TRVUX, work by creating marks on the surface of the sample, which imaging system then tracks in order to measure the displacement. And then the width is measured simply by recognizing the contrast of the material width in contrast to a black background. Here we see a stress-strain diagram and then also a width versus elongation diagram, and the slope of this plot is what's called the Poisson's ratio. This next test is kind of a combination of the previous 2 tests to study the strain characteristics of a separator film after it's been punctured. A tensile test was performed on a dog bone specimen with a puncture located in its center, and strain was measured with a video extensometer using a technique called digital image correlation, or DIC. DIC works by analyzing the movement of a speckle pattern on a sample's surface to measure and visualize strain across the entire surface. In the example below, the areas with the highest strain are displayed in red, which you can see is localized around the puncture location. In addition, we can also use the same test setup to study a separator's strain characteristics after repeated stresses. A sample similar to the previous slide was prepared and repeatedly elongated to 20 newtons of force for 20 cycles, and the displacement and strain were monitored. you can see that the sample elongates more with each cycle. And a test like this may also identify how a small puncture may spread or weaken the separator after repeated stresses. Overall, these applications show the versatility of a single instrument, a test frame with a video extensometer to perform several different characterizations of a separator film's mechanical properties. The next couple of slides will focus on tests possible with a microcompression tester, or MCT. An MCT is an instrument that can measure the force and displacement while compressing a sample using an indenter or a 50 micron wide compression plate. It can be used to test either small particles or to measure the micromechanical and surface mechanical properties of a material. In this instance, it was used to measure the compressive properties of a separator film in a load-unload test. This test can provide either the compression ratio, which is a measure of the amount a material compresses relative to its thickness under an applied force, or the recovery ratio, which is a measure of how much the material recovers after being compressed. 3 different separator films were tested. 2 were 20 microns thick and 1 was 10 microns thick. All 3 were prepared by adhering to a glass slide. Then they were compressed with a 50 micron flat diameter tipped platen to a force of 50 millinewtons. Here are the results of the compression tests. You can see on the right the force versus displacement curves for the 3 separators. And separator 1 was seen to have the highest compression displacement and compression ratio, while separator number 3, which was the thinnest separator, showed the lowest displacement and the lowest compression ratio. Since separators are incorporated into the battery with a large amount of pressure, this may be useful material characteristics to be aware of when manufacturing the batteries. Next is an example of a compression test of small particles. Since, as I said, the constituent materials of a lithium-ion battery are constantly being subjected to pressure during the manufacturing process and in use, it's important to evaluate the compression of the individual particles within the cathode and anode. This slide shows a compression test of a single particle of cathode material. As shown in the figure, the particles are spread out on a lower plate, and that lower platen is mounted to a micrometer base. And there's also, in addition to this side camera, there's also a built-in microscope in the MCT, which allows you to identify individual particles and test them individually. This picture shows an image of a particle of about 20 microns in diameter being compressed and to the point of fracture. In a normal compression test with an MCT, there are 2 types of strength measurements that can be evaluated. One is the fracture strength, which can be obtained when the particle fractures and an inflection point is observed on the graph. In the graph below, the vertical axis is the test force and the horizontal axis is the displacement. When a fracture occurs and the particle deforms rapidly, the displacement flattens out and the fracture strength is calculated from the inflection point. The other strength is called the reference strength, which is calculated from the test force and displacement at a point. It can be any percentage, but typically when 10% of the particle diameter is deformed. If the particles are crushed and deform without breaking, the graph will look like this at the break point. There won't be a clear break point like the fracture strength. So therefore, the reference strength is obtained by taking it up at a certain point of deformation. As an example, 2 different types of cathode materials were tested with the MCT. Samples were dispersed on the lower paten, and a single particle was tested using, identified using the microscope. The diameter of the particle is measured with the microscope. Then a compressive load was applied using a 50 micron compression platen up to 50 millinewtons. Here are the measurement results. The force is on the vertical axis and the displacement is on the horizontal axis. And fracture occurs at the inflection point where that force becomes horizontal. Two different materials were tested were lithium cobalt oxide and lithium manganese oxide particles. You can see that the lithium cobalt oxide particle fractured at 16 millinewtons, which is equivalent to a strength of 72 megapascals, while the same size lithium manganese oxide particle fractured at only 1.6 millinewtons, equivalent to a strength of 7 megapascals. In the final slide, I'll briefly discuss an application related to all solid-state batteries. So the liquid solvent-based electrolytes used in conventional lithium-ion batteries have several downsides. One is related to their flammability and difficulty in the manufacturing process. So there's an interest in using solid electrolytes, which can be compressed with the cathode materials in order to make an all-solid-state battery. Here's the results of evaluating the compressive properties of powder used to make fixed electrolytes. By measuring the fracture strength, we can compare the correlation with the ease of molding of the electrolyte. Comparing particles A and B shows that the fracture strength of particle B was about a tenth of the value of particle A, which indicates that the particles may adhere well to each other during the molding process. And the changes in the particle sizes from the processing may also influence the performance of the battery after it's been made. With that, I'd like to thank you for your attention, and I hope you enjoyed this presentation on evaluating the mechanical characteristics of lithium-ion battery components. Again, as I said, we'll be responding directly to any questions that have been submitted, so feel free to enter questions in the chat box, and we'll be getting in touch with you. Thank you.